I'm usually all about the serious applications, but every now and then something silly sneaks in, like this party decoration from a young kid's birthday I went to at some point. So it would be a pain to pack like this, right? To sell a pack of 10, you'd have to be very careful. They're very fragile, but they don't come this way. They come all collapsed. So how could we calculate the volume? The point here is to see that we are taking a kind of flat shape, in this case kind of a parabola, and we're stretching it out into the third dimension all the way around. Oh, you could see it sideways. So we could write a formula for that parabola and then imagine spinning it around the x-axis. So that's for fun little party decorations. So we'll say that's the ballerina tutu volume problem. Let's do something slightly more serious, industrial, maybe boring. How about a truck headlight? You know, a lot of headlights are filled with inert gas to keep the bulb going longer. So let's say it has the formula f of x equals 3 root x, x in the range 0 to 10 centimeters, the domain 0 to 10 centimeters. So if you draw that function, it looks something like this. It's a sideways parabola. And what's the value up here? It's 3 root 10, which is roughly, what, 9? Doesn't matter exactly. And we're saying take this shape and spin it around the x-axis. Does that look like it would be a headlight backing or a headlight reflector reflecting all the light that way? Reflector dishes like this are often parabolic because they give a nice, if you have the bulb here, all the reflected beams are going out fairly straight. So how do we take this volume of rotation? We're spinning it around the x-axis. I don't know if you can hear the fireworks in the background. It's almost 4th of July. So what's the enclosed volume? If we were going to fill this with some kind of inert gas, we would have to know what the volume is, right? Well, before we jump into the calculus of answering that, let's think about some quick lower and upper bounds, put some guide rails out there. So what's a lower bound on the volume? Well, I think you can agree the volume should not be negative. So we'll say a quick lower bound on the volume is 0. How about a quick upper bound on the volume? Well, we could say, back before when we did upper bounds on areas, we said let's enclose it with a rectangle. But here we're thinking about a 3D volume. What should we enclose this with? We could enclose it with a square, a cube or something, but I think a circular cylinder makes a little more sense. So we're going to say enclose it with a cylinder. So we'll draw the world's best drawing of a cylinder here. And what are its dimensions? Well, it would seem to have a height of 10 and a radius of 0 to 3 root 10. So 3 root 10 or 9-ish. So a volume of pi times 3 root 10 squared times 10, which is around 2,000 centimeters cubed. All right, we could do a guess, wouldn't hurt, because we know not all the area of that cylinder is filled up, right? There's this backing part over here. So it makes sense to do upper bound, lower bound plus upper bound over 2. And here it's hard to guess whether, it's hard to figure out whether the guess is above or below the actual answer, because we're trying to learn to think in 3D with the rotations and stuff. So it's hard to say if it's less than or greater than the actual volume. So part of the point of thinking about upper bounds and lower bounds is thinking about the 3D geometry of the problem, which actually is training our intuition to do better at imagining what's going on here, right? So it's not just establishing guardrails, it's thinking about the 3D problem in kind of a simpler way to begin with before we go deal with all the calculus of it. Let's write the actual integral. Our generic formula is integral a to b pi times f of x squared dx. So what is that specific to this case? We're starting at 0 and going to 10. That was on the x-axis up here. And then we've got pi times, and our radius function is just the function itself here, right? I forgot to draw the differential element, but that's usually a good idea. So we've got that, and we're spinning it around kind of behind the object and in front of the object. So it's a good idea to draw that imaginary, like one imaginary sliced disk that's spinning around. And what is its height, or what is its radius? It's f of x. F of x here is 3 root x, square it, times dx. And remember what we're saying here is area of the base times the thickness. And once we've got it in integral form, all the fun 3D thinking is done, and then it's just algebra and integral calculus, right? So you could simplify again, the square root cancels the square, or vice versa. So go ahead and finish it on your own, but that's not the interesting part. The interesting part is setting up the problem. And then another interesting part is once you get the answer, comparing it to your lower bound and upper bound and guess, and seeing, was it really half the upper bound, or was it more like a third of the upper bound, or a quarter, or something like that.